So our objective today is to learn about arcs and chords. We studied chords before. It's just a segment that passes through point or two sides of a circle. It doesn't have to pass through the diameter. The center would be a diameter then. And we've got a couple of theorems that go along with these. And theorems regarding arcs and chords. So this is lesson 9.4. So we're going to start straight away with a theorem. This is 9-4. Sadly, this chapter has very few named theorems. Okay, so this one says, in the same circle, or in congruent circles, and then we have two things that could happen. One, congruent arcs have congruent chords. And two, we have the converse, congruent chords. Oops. Have congruent arcs. Okay. So basically what they're saying here, that doesn't look real good, but you'll have to trust me. So this is T-U-S-R, circle O, and we're given, we have circle O, same circle, and if we have, in one case, arc RS is congruent to arc TU, we would be able to prove that segment RS is congruent to segment TU. So just to kind of give you an idea how that works,
please excuse this interruption. Michelle Barris, please contact the office. Michelle, please contact the office.
so basically what you would do is set up, if you have congruent arcs, let's see, I think how they would do this, I'm trying to think, I may have drawn my drawing not totally accurate, let me look. So we have radii, OT, OU, OS, OR, so all of those are congruent, and we need one more piece that's congruent, which would be, we have the arcs are congruent, so that's another key piece we can put in there from the given. If the arcs are congruent, then angle 1 would have to be equal to angle 2 because two arcs that are the same, their central angles are the same. Okay, that came from yesterday's notes. So then we would have side angle side to prove the two triangles are congruent, and then through CPCTC we would get segment RS is congruent to segment TU. Okay, so we would use the idea that angle 1 would have to be congruent to angle 2 because they're central angles whose arcs are congruent. Okay, so there's that, and then, yes ma'am.
In the given, is it supposed to be arc TU?
Oh yeah, that is supposed to be arc TU. I know, you spend so many chapters talking about segments, then all of a sudden you go to arcs, and it's a little bit of a relearning of the hand there, okay? All right, okay, so here's a statement that may help us with subsequent problems. Any line, segment, or array containing the midpoint of an arc bisects the chord and its arc. Okay, and that's going to come into play in our next theorem, so I wanted to throw that out first, and then here's our next theorem, 9-5. And it says a diameter that is perpendicular to a chord bisects the chord and its arc. Okay, so let's draw a picture of that one. So our given would be that we have a circle, we'll call it circle O, and we're going to have segment CD is perpendicular to segment AB. So let me draw the picture of the circle. So here's your CD, which is the diameter. Here's your AB, which is a chord. We're told that it's perpendicular. Those two are perpendicular to each other. Oops. Okay. We'll call that intersection point Z. Okay. And so what this theorem allows us to conclude if we have this condition, kind of based on the information that we had from before, is that we would be able to prove that segment AZ would be congruent to segment BZ, and then segment, or arc AD, the measure of arc just arc AD, because they're congruent, would be congruent to arc BD. So that D is the midpoint of the arc, and Z is the midpoint of the chord. Okay, and basically how they would go about proving this is by, again, creating triangles. They have a segment in common. They've got two radii in common, and they have right angles in common, and that would be actually HL, hypotenuse leg, would prove those two triangles are congruent, and that's how you could get that AZ is congruent to BZ, plus you could get angle OZ and angle BOZ congruent to each other through CPCTC, which would make our central angles congruent, therefore arc AD and arc BD would be congruent. Okay, so that's pretty cool. So let's do a couple problems like you'll see on homework tonight. So directions are going to say, for the first one, find the values of x and y. Oh, and y. So we'll call this CD. This arc is AB. This arc is EF. We're going to tell you that this arc measures 86 degrees. This chord measures 10. We're going to tell you this is perpendicular. This measure is 5. This measure is x. This arc is y. And there we go. Okay. So one of the answers we can get immediately just by looking at the information. What value do we know the answer to already? Yeah, what does x equal? It equals 5. And that comes from that theorem that we just talked about, theorem 9.5. A diameter that is perpendicular to a chord bisects the chord and its arc. Okay, the next piece we have to dig a little deeper. Okay, we still like that idea is not only does it bisect the chord, it bisects the arc. Okay, so then we look at if this x is 5, what's the length of AB? 10. What's the length of EF? So then this takes us back to the one that says in the same circle or in congruent circles, if you have two arcs that are the same, then their chords are the same. I mean, if you have two chords that are the same, then their arcs would be the same. That's not this one. Or it is in this one. Congruent arcs is theorem 9.4. So in the same circle, congruent chords have congruent arcs. So AB's arc which would be equal to the measure of arc AD plus the measure, we'll just call it Y. But based on what happened from theorem 9.5, the measure of arc AD and Y are the same thing. So this is actually equal to Y plus Y, or 2Y. And then the measure of arc EF is equal to 86. And these two arcs are equal to each other. So we've got 86 is equal to 2y. Actually, I should do that back the other way around. 2y goes with him, and 86 goes there. Divide by 2, and we get the measure of the arc is 43 degrees. So those would be the two answers. So notice that one answer is no label, and the other answer has a degree label. Okay? Okay, so this is arc AD. There we go. That makes more sense. And then same thing here. See, I tell you, this is so hard for me. I get so used to certain things. That makes more sense. There we go. Arcs and arcs. All right, so here's a different one. Find the length of a chord that is a distance 5 from the center of a circle with a radius of 8. Probably this is the most important thing, is to be able to interpret what I've just said, because you're going to see this show up a lot. So we're going to draw our circle. And we have a chord. We'll call it circle O. We'll call the chord AB. And the distance the chord is from, or the chord is from the center, that's your 5. Okay? Now, what could I tell about that piece that goes from O to that chord? What can I know about that? Isabel?
The O to the chord and then
Yeah. Okay, if I drew this out all the way, this would be theorem 9.5, which says a diameter would be perpendicular to the chord and bisects it, okay? So basically we could, bam, Okay, so it's going to be perpendicular. Now, we were told one more thing, that our circle has a radius of 8. And so our question is, what's the length of the chord? Well, in order to figure out the length of the chord, which I'm going to label as x, I'm going to only figure out half of the length of the chord, because that's all x is. X is halfway. And because I have a right triangle, I can use Pythagorean theorem. X squared plus 5 squared equals 8 squared. So we get 8 squared plus 25 equals 64. Subtract 25 from both sides. We get x squared equals 39. And we take the square root of both sides. And we get x equals square root of 39. There's no perfect square factors lurking in there. It's 3 times 13. But what we want to figure out is the length of chord AB. That's going to be 2 x's because we have the theorem that says that that's actually being bisected. That segment AB is being bisected. So then we get 2x would be the length of AB. So our actual answer would be 2 times radical 39. Okay? And then I've got one more theorem for you. All right, our last theorem. Theorem 9-6. And it says, in the same circle or incongruent circles, we've got 2 things. 1, chords equally distant from the center or centers if it's 2 congruent circles are congruent. So in that last scenario, you were told that your chord was 5 away from the center. If you had 2 chords that were both 5 away from the center, then the chords would have the same length. Or 2, congruent chords are equally distant from the center or centers. So the relationship is converse, works as well. So an example would be, here's 2 chords. There's circle Q. And this is chord UV. This is chord RT. I'm going to put some numbers in. I'm told this is perpendicular. I'm told this is perpendicular. This measures 4. This chord measures 6. This chord measures, or this point here is S. This is X. That 4 looks like a Y. Okay. So basically what we need to do, oh, we told this piece is 3. Okay. Because we have a line coming out of the center that's perpendicular to the chord RT, what that tells us is S would have to be a midpoint of segment RT. And so that makes the length of RT equal to 6. Well, that is the same as the length of UV. And so according to this one, our chords would be congruent, therefore they're equally distant from the center, so that means X would have to equal 4 from theorem 9-6. Okay? And then a lot of times what you'll be asked to do is then figure out what the radius of the circle would be. So go to the next step, okay? All right, good luck with your homework tonight.